discussed things in the section Lemma about sublevel sets or superlevel sets with respect to regular values, and a theorem that is of the kind, all the things we can prove for boundaryless manifolds that we did already. How does that generalize to manifolds with boundary? So let's start with a lemma on sublevel or superlevel sets with respect to regular values of the manifold. So let S be a manifold without boundary, and height probably for projection, so that's a height function. Be a function from S to R that is smooth, so a real valued function on a boundaryless manifold. Then let's pick a regular value. Let's take 0. Could be anything else. It's just a shift if you choose another regular value. Be a regular value. Then the lemma tells us that the sublevel set of this function with respect to 0, so this is all the points in the manifold such that the value is greater or equal than 0. So the preimages of all the positive values, including 0, are themselves a manifold. Well, and this time with boundary, and the boundary is exactly the preimage of 0. So pi minus 1 of 0, whichever other regular value you're looking at. Okay, so this here is, let's say, S, and our function to real values, let it be just the height function. Then if let's pick this as a level set and choose this as the preimage of 0. So is it a regular value? Yes, it is. No critical things there. So then what is S superior? These are all the ones that are preimages of this. So it's this upper part, and we stop here. So yes, this is a manifold of same dimension, and the preimage is its boundary. So that's what this lemma says. So how to prove that? Well, if we're in a preimage that is from like the higher than 0 points, then surely this is open. All of this without the boundary, this is open in S, so this is the submanifold itself without boundary. So that is good, and it has the same dimension. And for all the points for the subset that is strictly greater, this is open in S. So with strictly greater, this subset is a manifold without boundary, same dimension as S. And now for the ones where we actually are at 0. Well, since pi is regular close to S, then near S it's locally equivalent to a canonical submersion, so you can just look at it as a canonical submersion. Well, what for this? The lemma, or the statement of the lemma is clear, so. Okay. That's just a short argument. I think the picture is really what's nice to keep in mind. And yeah, you can use this lemma to show that all kind of things are manifolds with boundary. Nice example given is a ball. So example, if we take for S or Rn and as the smooth function 1 minus absolute value of S square, then this lemma gives us the closed unit ball, so that is the set of points S and Rn such that absolute value of S is small equal than 1. So this is now a boundary with manifold. Is a manifold with boundary, with boundary. Its dimension is n, and the boundary is exactly, well, the sphere on top of the ball. It's all the pre-images where S equals 1. Okay. The lemma is also used for the proof of the following theorem, which is, do I need more space? No, it's okay. Theorem. Theorem, a function from a manifold with boundary into a manifold without boundary. Smooth as always. And we want to know what is the preimage of a submanifold in Y under this function. And okay, we know for manifolds without boundary that this is again a submanifold. How does it look here? What would we expect? So what we would like. Next example would be, okay, let's take the upper half sphere as a manifold with boundary and as F, so X is upper half sphere. And let's take as a function just the inclusion, because then it's always easy to see that is transversal, or things are transversal and everything. So inclusion into R3, and R3 should be Y, so yes, that is without boundary, that's good. And now let's take a submanifold in Y. Okay, let's just take, I don't know, a plane here, and say what's the preimage of the inclusion map for this. So this is nothing else than the intersection, and that, okay, that is a interval. Well, I mean, it's this arc in the upper half sphere, these are the endpoints, so that would be indeed a manifold with boundary, and that boundary is something that looks like, okay, let's call that Z, and Z lives and Y is submanifold without boundary, and the preimage of Z, well, is this arc, boundary. So these 2 points are exactly where we hit the boundary of x. So that's kind of what we expect. And now you can stop and think about whether it's enough to take the same conditions that we had in the boundaryless manifold case, namely transversality of the function to z, or if we need a little bit more to ensure that also the boundary of the preimage comes in there and is a boundary as from the intersection. So if you have paused and come back, here is what we need. We need one little extra condition, namely we need that both the function itself is transversal to z and that the function restricted to the boundary of x is also transversal to z. So in your case, surely it is. This circle is transversal to this plane. But if not, it wasn't true. Now you can pause again if you haven't found an example and check that for this example it's not true. I draw it after writing down the theorem. So the theorem is if f, so f is from x to y, is transversal to z as well as the restriction, so the boundary, the map on the boundary, df or del f, and not boundary map. So the restricted one is also transversal to z. That's the extra condition that we need for boundary manifolds. Then we have exactly this situation. Then and now I should say what z is. Z is a submanifold. Submanifold of y without boundary. Okay, so then f minus 1 of z is a manifold with boundary, and the boundary is exactly given as the intersection of the preimage with the boundary of x. And the codimensions are also as expected. So the codimension of f minus 1z in x, so this one is the same as the codimension of z in y. So here this is 2-dimensional and this 3-dimensional thing, so codimension is 1. Here we have a 1-dimensional thing and a 2-dimensional thing, codimension is 1. So that's also, yeah. As things work without the boundary, only here we have this extra boundary thing coming in. But it's more like a restriction of this, and the cutouts are correct. So let's see the example where the function is transversal, but, well, not on the boundary. So in the simplest case, and where what goes wrong. So if I'm just taking here the plane where the circle lies in. Okay, so this is definitely not transversal because, well, the circle lies in this. So, I mean, every tangent is part of the tangent plane, right? So, okay. Now, what is a preimage? It's the entire circle. So let's call this that tilde. So yes, it's still a manifold. In this case, this is still nice, but this boundary thing doesn't work anymore. So it's not, the preimage is not a manifold with boundary. It would be a manifold without boundary. So that would be not, the theorem wouldn't hold in that case. This is not what the theorem says. Yeah. So transversal to this, and the preimage f minus 1 of that is, well, the whole boundary, and that we know is a manifold without boundary. So last comment, important but not surprising thing in the section is Sard's theorem holds also for functions on manifolds with boundary. So f, well, that's massive, from x to y, manifold with boundary, manifold without boundary, then almost every point in y is a regular value for both the function and the restriction to the boundary. Okay, how would you prove that? Well, you really just have Sard for two functions, and that's all good. And then both of them have only a measure 0 where things go wrong, and two measure 0 sets. I mean, yeah, there's really nothing that can go wrong. This is only like, I don't know, 3 lines writing this up. So we also have Sard, and that's all there is to say about manifolds with boundary, section 1.